Good day everyone. Today we are going to start with the part 4 of electrochemistry. Until now we have completed until the measurement of unknown resistance. So in this part we'll be starting with the molar conductivity. So the molar conductivity is a solution. Is the conductance of the solution containing 1 mole of electrolyte kept between 2 electrodes having unit length between them and large cross-sectional area so as to contain the electrolyte. In other words, molar conductivity is the conductance of the electrolyte kept between the electrodes of a conductivity cell at a unit distance but having the area of cross-section large enough to accommodate sufficient volume of solution that contains 1 mole of electrolyte. It is represented by this symbol, and the formula is K by C, which can be written as K into 1000 by M, where M is the molarity. The units of molar conductivity are as follows. Let us solve a question. The question states that the electrical resistance of a volume of 0.05 molar NaOH solution of diameter 1 cm and length 50 cm is given. So we have to calculate the resistivity, conductivity and molar conductivity. So we know the area is pi r square. So placing the values we get the answer to be 0.785 cm square. The resistivity formula is Ra by L. By placing the values we get the answer to be 87.135 rho centimeter, ohm centimeter. And the conductivity is the opposite of resistivity. So we get the answer to be 1.148 into 10 to the power minus 2 ohm inverse centimeter inverse. The molar conductivity formula is K into 1000 by M. So by placing the values we already know the conductivity. So we get the answer to be 229.6 Simon centimeter square per mole. Now we'll be studying about the variation of conductivity and molar conductivity with respect to concentration. So the conductivity of a solution is the conductance of a unit volume of the solution kept between 2 platinum electrodes with unit area of cross section and are separated with a unit length. It is represented by the following formula. So it always reduces with reduce in the concentration of both the strong and weak electrolytes. This is due to the fact that the number of ions that carry the current in a unit volume of solution will always reduce with reduce in the concentration, while the molar conductivity is the conductance that of the one volume of the solution which contains 1 mole of electrolyte. It is represented by the formula. So the molar conductivity will increase with reduce in the concentration. This is because the total volume of the solution containing 1 mole of the electrolyte will increase. So when the concentration approaches 0, the molar conductivity will reach a limiting value known as limiting molar conductivity. It is represented with naught. So let us discuss for strong electrolytes. So practically strong electrolytes will completely ionize at all concentrations. For strong electrolytes, the molar conductivity will increase with increase in the solvent. This is represented by this following equation, which is that the molar conductivity is equal to limiting conductivity minus A root C. Here A is the constant that will depend upon the viscosity and dielectric constant of the solvent, while C is the concentration of the solution. So here we can plot a graph with molar conductivity against root C. We get a straight line with a slope as minus A and intercept as the limiting molar conductivity. So the value of constant A will depend upon the type of electrolyte, that is the charges on the cation and anion produced on the ionization of the electrolyte in the solution. So this graph basically shows us the variation of the molar conductivity with root C for KCl, which is a strong electrolyte. Now we'll study for a weak electrolyte. So the electrolytes which do not completely ionize in aqueous as well as molten state are called weak electrolytes. A weak electrolyte do not get ionized completely at all the concentrations. On dilution, its alpha will increase and resulting in an increase in the number of ions. So the limiting molar conductivity value of weak electrolyte will increase steeply with dilution, especially in low concentration regions. So we can basically plot this kind of a graph against the molar conductivity with root C. This graph is for CH3COOH, which is a weak electrolyte. But the proper explanation can be provided by Kohl-Rosch's law, which we'll study in a while. First, let us see the formula of the degree of association, which is alpha is equal to molar conductivity by limiting molar conductivity. And we also have a constant whose formula is C alpha square by 1 minus alpha. Now we'll study what is Kohl-Rosch's law. He explained the limiting molar conductivity values for a number of strong electrolytes and found that the pair of electrolytes with same negative ion but differing only in the positive ions, then the value is a constant, the value of limiting molar conductivity. Similarly, with the common cation, the difference of the limiting molar conductivity values is also found to be constant. So the above observation led to formulate the Kohl-Rosch's law of independent migration of ions. So this states that the limiting molar conductivity of an electrolyte is the sum of the individual contributions of the cation and anion of the electrolyte. We can represent it as follows, that is, the limiting molar conductivity of NaCl is the combination of Na plus and Cl minus, these both individual contributions, which can be represented with a general formula as follows. Now we'll study the applications of Kohl-Rosch's law. That is, the molar conductivity of weak electrolytes at infinite dilutions can be calculated, and we can calculate the alpha at a given concentration, and we can know the alpha and also the constant K, and the solubility of the sparingly soluble salts like BaSO4, AgCl, MgO2, OH2 are calculated as solubility. And the molar conductivity of weak electrolyte also depends on alpha. Higher the value of alpha, higher will be the molar conductivity. Let us solve a question. So here we have to calculate the limiting molar conductivity for acetic acid. We are provided with the limiting molar conductivities of HCl, NaCl and CH3COONa. So here we can find out that for CH3COOH, we can find with a combination of H plus and CH3COO negative. So by placing the individual ions and adding and subtracting the values, we get the answer to be 391 Simon centimeter square per mole. Now let us give a quick ncert reading. In this part, we have started with the molar conductivity, and we have also completed the variation of conductivity and molar conductivity with respect to concentration, and we have studied for the weak electrolytes and strong electrolytes and the Kohl-Rosch's law, which is the law of independent migration of ions, and we have also studied the general formula, and the applications of Kohl-Rosch's law is also done. So in the next part, we'll be starting with the electrolytic cells and electrolyte and the working of electrolytic cells. Thank you so much for watching. Stay tuned for more updates.